Okay. For example, remember that's the equation of a circle. What's the center of the circle? What's that? Yeah, but what is it on that one? Just looking at it. Come in. So what is the center of this circle? 1, negative 3, right? So you say 1, negative 3. And the only other thing to know about a circle is what's the radius? 2, right? This is r squared. So r equals 2, square root. Okay, given any old equation like that, how do you find x and y intercepts? Right, to find the x-intercepts, okay, again, talking to myself, so substitute y equals 0. To find the y-intercept, substitute x equals 0. So in this case, when I substitute y equals 0, I get 0 equals 4 minus x squared equals 4. So x equals plus or minus 2. Those are the x-intercepts. To substitute x equals 0, I'm going to get y equals 4 minus 0, y equals 4. Right? That's always the way to find x and y intercepts. Right? Just substitute the other variable equals 0, because that's what it equals on that axis. Right? There is a fairly basic solve an equation. It's a linear equation, something like this. It's taken from the prerequisite sections in that orange book. So it's not intended to be overly difficult, but we should know how to solve a basic linear equation. In this one, use distributive property, get everything on one side. I think I'll skip over that one. All right, solve an inequality. What's the only thing you've got to worry about with an inequality that's different than an equation? Multiplying and divide by negative. Okay, solving absolute value greater than and absolute value less than. Right, always the first step would be isolate. In these, it's already isolated. I believe on the test it's already isolated too. So at that point, you just have to take the next step. Right, the next step being for a absolute value less than, make a 3-part inequality. For a greater than, it is to write 2 inequalities. And tie them together with the word or. If you deal with the first one with 2 different inequalities, you could still get it right, but you've got to be careful that is both x minus 20 is less than or equal to 4, and the word and, negative 4, x minus 20 is greater than or equal to negative 4. And you've got to have that word and in there, or else it wouldn't be right. Most of the time on tests, they're not going to do that with 2 different inequalities. you have to be able to use these three-part inequalities. Right? Now, when you solve the three-part inequality, that means you're going to isolate the variable in the middle by doing operations to all three parts. Like in this one, I would have to add 20 once, twice, 3 times. So that's 16 less than or equal to x less than or equal to 24. Right, this one would be x is greater than or equal to 24, or x is less than or equal to 16. Right, determining from an equation whether or not it represents a function. And the only thing to look at there is, not the only thing, if there's a y squared, it's not a function. Because when you solve that for y, for example, this one here, I would get y squared equals 4 minus x squared. And when I solve for the y by taking the square root, I would get y equals plus or minus 4 minus x squared. We know the definition of a function is for every x value, you get one y value. Well, here clearly you're going to get 2. You're going to get the plus and the minus. So this is the not. Right. Now the second one, x squared plus y, because it's just y to the first, you don't have the same issue. That's a function. Right. A horizontal line is definitely a function, but a vertical line is not. Right? Vertical line would not pass a vertical line test. Evaluate functions. Right? If you have the definition of a function, in this case, h of t equals t squared minus 2t. How do you find h of anything? In this case, h of 2, h of a number, in place of the t, put a 2. But you could have something other than a number in there. It's still whatever is in the parentheses, whatever you're evaluating, put it in the place of the variable. That would be x plus 2 squared minus 2 times x plus 2. Right? I've just put that x plus 2 here and here. And that could be simplified. X squared plus 4x plus 4 minus 2x minus 4. X squared plus 2x. So evaluate functions. Domain and range from a graph. Right? If it's a simple parabola, if it looks like the graph is going forever to the left and right, that those are arrows, then you would say the domain is all reals. The range, clearly this graph does not go forever up and down. It starts at y equals 0 and goes up to the left and the right. So the range is y greater than or equal to 0. Which on these tests, you should expect that they're probably going to use the interval notation. It would look like 0 to infinity. Right? The left side of that interval is 0, and it includes 0, so it's in a square bracket. The right side is infinity. Infinity always is around bracket because you never get there. Right? A graph like this, you should recognize the shape as a square root. That's what a square root function looks like. Right? It does not look like the domain is all real numbers. It looks like in terms of the x values, it starts at x equals 0 and it goes to the right from there. So we can say 0 to infinity, x greater than or equal to 0. And in the terms of the y values, it does not go infinitely up and down. It looks like it starts at y equals 2 and goes up from there. Let me do it. Be consistent. This thing has been crazy today. 2 to infinity. right? Determine functions by looking at a graph. Does it pass a vertical line test? Right? Something like this. You know, if you cannot imagine that a vertical line could cross in more than one spot, then you say passes vertical line test. Yes, function. Right? But if you can imagine anywhere on the graph, it doesn't have to be for every point on the graph. In this case, actually here, if I passed a line here, it would only cross once, just right there. But that doesn't matter because somewhere else on the same graph, it crosses twice. So you say, not a function. Easy stuff. Right? Intervals of increasing and decreasing. Intervals, when they say intervals, it's always intervals of x. In this case here, this graph looks like it's increasing in that interval from the left side until it gets to that line. It's decreasing from there to about there. It's constant in between 0 and 2, it looks like, and then it starts to increase again. Right, so you want to say that it's increasing from the left side. You're not using where it crosses the x-axis. You're not like trying to go there. You assume this goes forever to the left. This interval would start at negative infinity, and it would get to 1 to negative 3. And it's round because it's not right at negative 3. It's not increasing or decreasing. But you don't want to use y equals 1, right? This is in terms of x. So negative infinity to negative 3. This interval here would be negative 3 to 0. Right, we'll leave the constant interval alone and then say this one starts at 2, and the right side would be infinity. Now, even and odd we didn't do a lot with. Maybe not anything. I would prefer not to even deal with it, but an even function, which I've just shown this absolute value function right there, is symmetric with respect to the y-axis. It should look like it's the same on one side as it is on the other. Symmetric with respect to the y-axis, right? Left and right. And an odd function, it's not that it's symmetric with the x-axis. That might be what you'd like to think, but it's not that. What it is that it's actually, you would say it's symmetric with the origin, which means that it definitely has the origin on it. And then for every point you have in one quadrant, you should have a corresponding point in the opposite quadrant. So this one looks like it has got a point, maybe it's around negative 1, 1. Then you should be able to go to 1, negative 1, and there should be a point. So everything is reflected in opposite quadrants. That's a hard one sometimes to see. Right? Describe transformations. Again, you should recognize this graph as a square root function, which normally the parent function would be here. Right? So what are the shifts, the transformations that have gone on? It looks like it's 1 to the right, 2 down, and it's flipped. Right? So how do you make a function go 1 to the right? You subtract 1 inside the function. How do you make it go 2 down? You subtract 2 after the function. How do you flip it? Put a minus in front. And same thing, this is a parabola, and the transformations are left, plus 2 inside means left, minus 2 outside means down. The minus in front means a flip, And the 1/4, if we multiply by a number that's less than 1 in this book is called a shrink. If it was bigger than 1, you call it a stretch. Okay, and I think the reason that I pointed to these here is because I think the problem that you've got is actually a cubic, right? And a cubic function, I don't believe it really matters what the cubic function looks like. The parent function looks something like that. But it's still, you're looking at a graph, an equation which has got transformations in here. They work the same for every kind of function. So that's stretch, that's left, that's down. Okay, there's going to be some adding or subtracting or multiplying of functions. Given two functions, how is it that you add them up and evaluate? Well, the f plus g of 3 would be f of 3 plus g of 3. Right? If that said f plus g of x, it would be f of x plus g of x. Okay, now substitute for those things. F of 3 would be 3 squared plus 1, which is 10. G of 3 would be 3 minus 4, which is negative 1. So that's 9. And you might also have a subtract, or you might have a multiplication. I don't remember which one it is, but it's one of those, because that's what these problems were. Just remember, when you do that, you're plugging into these functions. You're not also multiplying times 3. That is not a multiply times 3. That's function notation for f of 3, g of 3. Right? Don't go back and try to multiply by whatever that is. We had another operation, which is called a composition. Right? Composition is that little open circle. F of g of x. Again, that's not a multiply, that's a function notation, is f of g of x. Right? And, substitute for the g of x, x minus 1, and then evaluate the f function, f of x minus 1. Again, when you evaluate a function, you just put whatever's in the parenthesis in the place here. Essentially, you're taking that inner function here, and you're plugging it in there. So that will look like x minus 1 squared. Okay, inverses. Find an inverse. Right, to find an inverse, first step would be replace the f of x with a y. Switch the x and the y. Solve for y. Right, in this case, because the y is inside the square root, we square both sides. We subtract 3. Divide by 2. Okay, now, this is the f minus 1 right there. This, again, is a square root graph. We know what a square root graph looks like. It's going to have some kind of a shape like that. Right? That's a parabola, which should have some kind of a shape like that. Right? Those two cannot be inverses of each other. Right? They should look like they are reflections across the line y equals x. And there's no way that these could look like that. But that's why you've got to take into account domain and range when you do inverses. Right? Remember, when you switch the x and the y, that's like saying switch the domain and the range. Right. This thing, because it's a square root, you assume that it's positive. So the range of this function was y greater than 0. That means the domain of this is x greater than 0, which means we're not going to actually have the entire function. We're just going to have the right side of that parabola. And those two, if I put them on the same background, might look like they're flips of each other, but not the whole parabola. So, usually the way this would be stated, you might get this right here, and then afterwards it's going to have to say something like x is greater than, that was actually greater than or equal to 0 to be complete. I don't think they're trying to trick you with the problem like that, but just remember these steps. How do you find an inverse? How do you find an inverse of a table of values? Again, inverses and functions, you switch the x's and the y's. So if this is the x values for the function, then they must be the y values for the inverse, right? And the y values become the x values of the inverse. Okay, find a vertex x and y intercepts of a parabola. And in this case, there's two different parabolas there, right? One of them, two different quadratics. One of them is already in a standard form, a vertex form. The other one is not. You should be able to say what the vertex is of this one because it's already in that form. And that would be, and we did in this semester, we did both quadratics as functions, in which case we had this was our equation for a quadratic. Y equals a times x minus h squared plus k. And then later when we did the section on conic sections, it was slightly different. It was actually x minus h squared equals 4p y minus k. So at this point, because of where we are in the book, we're actually more interested in this thing right here. This has a vertex, since the h has got a minus in front of it, this is minus 6, then the h is a positive 6. That k is positive when it's on that side of the equation, right? Unlike that one. So it is a positive 3. And then in terms of x and y intercepts, again, you've got to do what we did on the second slide that we had, second or third slide. To find an x-intercept, substitute the y equals 0 and solve. Right? In this case, you would have 0 equals x minus 6 squared plus 3. Solve. To find the y-intercept, substitute x equals 0. That will be x. All right, then we're going to go y equals 0 minus 6 squared plus 3, and solve. If it's not in the vertex form, you either have to put it in that form, for the which we can do in different ways. You can calculate the vertex, remember, by doing h equals negative b over 2a. That would tell you the h. And then you would find the k by putting that back into the function. That's actually factorable. X squared plus 2x plus 1. I mean, we could write that one down right away and say that's x plus 1 squared. So I could say in this format now, the vertex is negative 1, 0. When you have an equation like this that's in this general form, then this plus 1 right there, that is the y-intercept. When it's in that form, that's not the y-intercept. Don't think that that's the y-intercept. Right? You still have to substitute 0 here. That's going to be 36 plus 3, 39. But that one you could tell right away. That's the y-intercept. In terms of the x-intercept, we'd put a 0 there. We could tell the x-intercept is -1. Right? You can also, you can have a calculator. Remember, you can put them in the calculator. Just look. Look for the x and the y-intercepts. There is one that is a word problem. It says find the minimum or find the maximum. If you remember, if a parabola opens up, then the vertex of it is a minimum point. Now, how do you know whether it opens up or down? By whatever the coefficient of x squared is. If that's positive, it opens up. If it's negative, it opens down. Right? If it opens down, then the vertex is a maximum. So when a problem asks for a minimum or a maximum, they're asking for the vertex. Right? And how do you find the vertex? H equals -b over 2a. You substitute into that formula. In this problem here, the -b, this is the b. This is a, this is b, this is c. Right? The b is -10, so this is -10 divided by 2 times 0.25, which is 10 divided by 0.5, which is 20. So the x-coordinate of the, in this case, it's positive, so we're definitely looking at a minimum. The x-coordinate is 20. Right? If you have to find the y-coordinate, then plug that back in here and here and solve. Right? So min and max is the vertex. Use this. Okay, that's as far as I got on that. 171. 63 to 68. Right, the directions on these problems say, find all the real solutions to this equation. You got to remember that polynomial equations like this have how many solutions? It's whatever is the degree of the polynomial, meaning the highest power, that's how many solutions it's got. Okay. But you don't know if they're all real. So it's asking for find the real solutions. You're not necessarily finding 5 solutions. Remember, complex numbers are the big set of numbers. Right? They consist of real numbers and imaginary numbers. Right? Every polynomial equation has got exactly as many complex solutions as that number right there, the degree. Right? The real solutions, look at the graph. Real solutions show up as x-intercepts on the graph. So look at the graph for that. X-int on graph. Okay. Imaginary solutions then are the ones that aren't real. They're going to have to be imaginary. Remember, the one thing that we know about imaginary solutions, because imaginary solutions ultimately come from quadratic formula, and the quadratic formula in front of the square root has a plus or minus. They come in pairs. There's always an even number of imaginary solutions. right? And it should be the number of complex, which you know that one right away, minus the number of real, that'll be the number of imaginary solutions. If you look, let's say you're looking at this graph, and right away you say, there's 5 solutions, 5 total solutions. And then you looked at the graph, and it looks something like this. Right? That is a 5th degree polynomial. It's got 4 turning points on it. And how many real solutions do you see? You definitely see something there, and you see something there, which, if you add that up, that's 2. Well, if there's 5 total and 2 real, how many imaginary does that leave? 3. But that can't be, right? Because the number of imaginary is always even. Remember, when a graph touches the x-axis and then goes back in the same direction, that's actually a sign that that 0 is there twice. So this one would have been there twice. This one is once when it passes right through. That's a total of 3 real. Okay. Now, leave it at that. So do the graph. Remember, on the calculator, if you put a function, if you go up here and put your equation right there, then you're going to be looking at the graph to see where it crosses the x-axis. If you want to know exactly where it is, you got to go to second, trace, 2 for 0. Okay, that's the way you find it. You want to get exact about where it's at. That's how you find it. Okay, 5966. Right, operations with imaginary numbers. Negative 6i squared plus I to the 3rd. And you know, these were the ones that I thought were most like the ones on the test. I think the one that's on the test is something like I to the 50th. It's just a power of I, which in the end you're supposed to know. What they expect that you would know is that I to the 1st is I squared is -1, I to the 3rd is -I, and I to the 4th is +1. And then it just repeats that pattern every multiples of 4, right? Every multiple of 4 power of I equals 1. If it's an even power of I but not a multiple of 4, it's -1, right? If it's 1 more than a power of 4, then it's +I. If it's 1 less than a power of 4, then it's -I. Something like 50, you say, well, that's an even number, but it's not divisible by 4, so it's -1. But remember, your calculator will do this for you. Right? You can go to the calculator and put in I. Remember, in the mode, this is not always necessary. And I don't know if it's necessary now, but if you get an error, you can set the calculator to do imaginary right there, A plus BI. Right? And then on the main screen, the I is above the decimal point. So that goes second I raised to the 50th. I get the -1. Sometimes when you do operations with I, you get scientific notation back. Scientific notation, which is actually every time that's there, it really means 0. It's just that the calculator is not rounding it off. And you have a way to deal with that too. If you do operations, not there. If you do operations for the imaginary numbers, go math, num, and use this I part. Put whatever your calculation is there. It will never give you those scientific notation representations of 0 that confuse us so much. But again, you can enter these in the calculator. If you need to do that, by all means, get it right. Don't be trying to prove a point. 187, 9 to 12. 9 to 12. Okay, for example, we already talked about this. F of x equals x to the third minus 4x squared. If you look at that graph, it looks something like this. And these problems are really just, they're asking about the number of real zeros, the number of complex zeros, the number of imaginary zeros. You would look at this and say, well, there's got to be 3 complex, there's 1 real, so there must be 2 imaginary. Right? That's how you look at a graph. And you will be asked that kind of question. You know, it's not about what's the value of the zero, it's just how many zeros of each kind do you expect. Hey, what did I say about hey? Yeah. So these are, I specified in here that it's only the letter A part. There's actually 3 parts, A, B, and C. But the only part that we're being asked about is what is the domain? If you look at that, you just have to make sure you don't divide by 0. What is the one value of x that would lead to a divide by 0? Right? You have to say x does not equal 2. That's it. It may be, and it may be they use a term like that to say what is the point of discontinuity also. If they do, I mean, it's still the same thing. The point of discontinuity, because since x cannot equal 2, right, the graph can't cross that line. So you would have 2 different parts of the graph. So that is also a point of discontinuity. Okay. And these problems look like this. 3.4 to the 6.8. And probably more important would be something like e to the 9.2. Right? It's at the very beginning of when we deal with exponentials and logarithms. And these are the problems that just say use your calculator to evaluate. That's all it says to do. Right? So do you know how to do that in the calculator? Right? The 3.4 is easy. Right? And then how do you raise it to a power? You go up here. Right? So then you put in the 6.8. What about E? Where do you find E on the calculator? I'm pretty sure that the test question's in E. So where is the E? E is above the divide right there. So you could either take that. You could also notice that above the ln it says e to the x. If you go over there, it actually already puts you into the exponent. Second ln and then 9.2. So just be able to use the calculator to evaluate an exponential like that. 15 to 22. Okay, these are graphs. And again, remember, exponential functions have 2 parent functions. Right. One of them looks like this. One of them looks like this. Right? One of them is exponential growth. One of them is exponential decay. Right? Both of them have asymptotes on the x-axis, meaning it'll approach that line, but it'll never touch it. Right? Both of them have y-intercepts at 1. Both of them have domains of all real numbers. both of them have ranges which are greater than 0. The question is graphing by transformations. So for example, if I had let's say I have this function, y equals 2 times 3 to the x minus 1 plus 4. Right? We would expect that one is exponential growth because that number is bigger than 1. We would expect the minus 1 inside the function to be a right shift of 1. We would expect the plus 4 to be a up. And then the 2 is a stretch. They mean all the same things with this function that they meant with any other function. So I believe on the test, it's picking out a graph, which is the appropriate graph of a function that you've been given. So you just have to be able to identify it. All right? $236. Numbers 19 to 22, and it says calculator. That doesn't seem right. 19. I got to check my, what I'm writing down here, because I have a feeling that is not exactly what I meant to say. It's all mostly about the same anyways, but let me check, make sure that wasn't supposed to be from this page. And it's not. 15 to 22. Okay, well, that's all right. 19 to 22. The 19 to 22 on 236, oh, that's okay. Log, sorry, I messed that up, not you. Log base 2 of 16. On the test, what it says is use change of base formulas to calculate that, right? Change of base formulas mean since you don't have log base 2 on the front of the calculator, then you can put it in as log base 10 of 16 over log base 10 of 2. But remember that actually these yellow calculators, at least, they do have logs of any base in it. So there's really no reason to have to do the change of base part, even if it's, it's a multiple choice test. Whichever way you want to do it. If you want to write it like this, put it in the calculator, you'll get it right. If you want to go to the calculator, remember that the log base is under the math menu, all the way at the bottom there, the letter A, log base. That lets you enter a calculator, a logarithm of any base. So when you get to that problem, that's what you want to do. Okay, 236, 31 to 34. And this is more just evaluate with a calculator. I mean, even here it says evaluate with a calculator. What if it says ln of 4 plus the square root of 3? Then just put it in the calculator, right? You've got ln on the front of the calculator right there. ln in parentheses 4 plus the square root of 3. That was wrong. Delete. Second square root of 3 in parentheses. $254. $24 and $25. Right? So these are solving logarithms mean, there's a reason why that the study is pointing you to two problems which are almost the same. And that's because the test question is going to be almost the same as this too. So solving when you've got a logarithm minus this logarithm equals 0, which means if I just add log 2 to both sides, I would have a logarithm equals a logarithm. Right? That was called a one-to-one property. If a log equals a log, then it must be what's inside is the same. So it must be that x equals 2. Okay, not one where we have to like start doing complicated things to solve. Just try to make the left equal what look like what's on the right, and then make an equation out of the arguments. 620. Okay, 625. So now we're getting into the sequence and series stuff that we just did. 23 to 28. Okay. Here's a formula for AN. Find A25. Right? Given a formula, can you find one term in the sequence? What would you do with the 25? Right? You would take that 25 and you'd put it in there, and you'd put it in there. That's all they're asking you to do. Right? Be able to just find a particular term in the sequence given the formula. And as I remember, it's not actually something like this with -1 raised to powers. It's not a factorial. It's actually arithmetic or geometric. Just they didn't have any questions in those sections that were like this, that they just give you the formula, they find this one term. So that's why I pointed to this one here. Right? So 645, 69 to 72. Okay, these are like this, the sum, 0 to infinity of 2 times 2/3 to the n. Find the sum. Now, you'll have the formula sheet with the formulas on it. This is an infinite geometric. Right? You know it's geometric because it looks exponential, and it's infinite because it goes until infinity. There's the infinity symbol. Right? The formula we have for that is S equals A1 over 1 minus R. So when you're looking at that kind of notation, the R is whatever's being raised to the power. And then how do you find the A1 to plug in there? You take this bottom lower limit and you plug it in for n. So the A1 in this case would be 2 times 2/3 to the 0, which is 2. Now, can you always use that formula? No. Only when the absolute value of R is less than 1. You know, if you're given the terms in a sequence and you can just see them, it didn't tell you the R. If you know it's geometric and the terms are getting smaller, then you can use it. The terms got to be getting smaller. 710. Okay. Okay. Okay, this one is I believe it asks for the center, and it asks for what kind of a shape is it. If you remember, there was 4 kinds of conic sections that we studied. One of them we already dealt with. The very first slide was a circle, right? Circles, parabola, ellipse, and hyperbola. Okay, so when it comes to the type this is, we know it's not a circle. Remember, circles have the same coefficient in front of both. We expect it to have a r squared on the right-hand side. We know it's not a parabola because parabola only has one squared term. So then it comes down to, is it an ellipse or a hyperbola? And remember that hyperbola, they have opposite signs. I mean, from the definition, hyperbola was the set of all points, the difference of whose distances from two fixed points is constant. For an ellipse, it was this sum, right? So this is definitely an ellipse. And the center, just like we found the center of a circle, would be -2, -1. Done. What if it was x squared over 16 plus y squared equals 1? What is the center? 0, 0. Since you don't see anything being subtracted, the center is 0, 0. Yeah. The origin. And then this is the last. If you go to this one, 721, this is where they gave us, you know, when you're looking at these equations that have, they're quadratics, they could have an x squared term, they could have a y squared term. Just determine from those two terms what kind of quadratic or conic section are you looking at. Remember, ax squared plus by, sorry, that's not by squared. Just if the A equals C, circle. Right, if these two are the same, it'll be a circle. If the A or C equals 0, meaning you only have one squared term, parabola. If A and C opposite signs, hyperbola. And the last is A does not equal C, but they do have the same sign, then it's an ellipse. And I've put these problems on, you know, it's one question. It's one question that asks you, like, what kind of shape is it? What's the center? Something like that. And again, these are the problems to study. It's a study guide. It's not, I'm not picking it up for extra credit or anything. This is incorrect. This is 106. Right, I would, you know, try to do some of them. You're going to say, I know how to do that, just move on. The ones you don't get, you know, try some, check the answers in the back if you can. I'm here every day before and after school, Saturday, 10 till noon.